Fiber-optic communication is a method of transmitting information from one place to another by sending pulses of infrared or visible light through an optical fiber. The light is a form of carrier wave that is modulated to carry information. Fiber is preferred over electrical cabling when high bandwidth, long distance, or immunity to electromagnetic interference is required. This type of communication can transmit voice, video, and telemetry through local area networks or across long distances. Optical fiber is used by many telecommunications companies to transmit telephone signals, internet communication, and cable television signals. Researchers at Bell Labs have reached a record bandwidth, distance product of over 100 petabit times kilometers per second using fiber-optic communication. First developed in the 1970s, fiber optics have revolutionized the telecommunications industry and have played a major role in the advent of the information age. Because of its advantages over electrical transmission, optical fibers have largely replaced copper wire communications in backbone networks in the developed world. The process of communicating using fiber optics involves the following basic steps. Creating the optical signal involving the use of a transmitter, usually from an electrical signal. Relaying the signal along the fiber, ensuring that the signal does not become too distorted or weak. Receiving the optical signal. Converting it into an electrical signal. Optical fiber is used by telecommunications companies to transmit telephone signals, internet communication, and cable television signals. It is also used in other industries, including medical, defense, government, industrial and commercial. In addition to serving the purposes of telecommunications, it is used as light guides, for imaging tools, lasers, hydrophones for seismic waves, sonar, and as sensors to measure pressure and temperature. Due to lower attenuation and interference, optical fiber has advantages over copper wire in long-distance, high-bandwidth applications. However, infrastructure development within cities is relatively difficult and time-consuming, and fiber optic systems can be complex and expensive to install and operate. Due to these difficulties, early fiber optic communication systems were primarily installed in long-distance applications, where they can be used to their full transmission capacity, offsetting the increased cost. The prices of fiber optic communications have dropped considerably since 2000. The price for rolling out fiber to homes has currently become more cost-effective than that of rolling out a copper-based network. Prices have dropped to $850 per subscriber in the US and lower in countries like the Netherlands, where digging costs are low and housing density is high. Since 1990, when optical amplification systems became commercially available, the telecommunications industry has laid a vast network of intercity and transoceanic fiber communication lines. By 2002, an intercontinental network of 250,000 kilometers of submarine communications cable with a capacity of 2.56 TB/s was completed, and although specific network capacities are privileged information, telecommunications investment reports indicate that network capacity has increased dramatically since 2004. As of 2020, over 5 billion kilometers of fiber optic cable has been deployed around the globe. In 1880, Alexander Graham Bell and his assistant Charles Sumner Tainter created a very early precursor to fiber optic communications, the photophone, at Bell's newly established Volta Laboratory in Washington, D.C. Bell considered it his most important invention. The device allowed for the transmission of sound on a beam of light. On June 3, 1880, Bell conducted the world's first wireless telephone transmission between two buildings, some 213 meters apart. Due to its use of an atmospheric transmission medium, the photophone would not prove practical until advances in laser and optical fiber technologies permitted the secure transport of light. The photophone's first practical use came in military communication systems many decades later. In 1954, Harold Hopkins and Narinder Singh Kopani showed that rolled fiber glass allowed light to be transmitted. Junichi Nishizawa, a Japanese scientist at Tohoku University, proposed the use of optical fibers for communications in 1963. Nishizawa invented the pin diode and the static induction transistor, both of which contributed to the development of optical fiber communications. In 1966, Charles K. Cow and George Hockham at Standard Telecommunication Laboratories showed that the losses of 1000 dB/km in existing glass, compared to 5 to 10 dB/km in coaxial cable, were due to contaminants which could potentially be removed. Optical fiber with attenuation low enough for communication purposes, about 20 dB/km, was developed in 1970 by Corning Glass Works. At the same time, GaAs semiconductor lasers were developed that were compact and therefore suitable for transmitting light through fiber optic cables for long distances. In 1973, Optical Incorporated, co-founded by the inventor of the laser, Gordon Gould, received a contract from ARPA for one of the first optical communication systems. Developed for Army Missile Command in Huntsville, Alabama, the system was intended to allow a short-range missile with video processing to communicate by laser to the ground by means of a 5-kilometer-long optical fiber that unspooled from the missile as it flew. Optical then delivered the first commercial optical communications system to Chevron. 21. After a period of research starting from 1975, the first commercial fiber-optic telecommunications system was developed, which operated at a wavelength around 0.8 μm and used GaAs semiconductor lasers. This first-generation system operated at a bit rate of 45 Mbps with repeater spacing of up to 10 km. Soon on April 22, 1977, General Telephone and Electronics sent the first live telephone traffic through fiber optics at a 6 Mbps throughput in Long Beach, California. In October 1973, Corning Glass signed a development contract with Xult and Pirelli aimed to test fiber optics in an urban environment. In September 1977, the second cable in this test series, named COS2, was experimentally deployed in 2 lines, 9 km, in Turin, for the first time in a big city, at a speed of 140 Mbps. The second generation of fiber optic communication was developed for commercial use in the early 1980s, operated at 1.3 μm and used in GaAs semiconductor lasers. These early systems were initially limited by multi-mode fiber dispersion, and in 1981 the single-mode fiber was revealed to greatly improve system performance. However, practical connectors capable of working with single-mode fiber proved difficult to develop. Canadian service provider SASKtel had completed construction of what was then the world's longest commercial fiber optic network, which covered 3,268 kilometers, 2,031 miles, and linked 52 communities. By 1987, these systems were operating at bit rates of up to 1.7 Gbps with repeater spacing up to 50 kilometers, 31 miles. The first transatlantic telephone cable to use optical fiber was TAT-8, based on D-Servier optimized laser amplification technology. It went into operation in 1988. Third-generation fiber optic systems operated at 1.55 μm and had losses of about 0.2 dB/km. This development was spurred by the discovery of indium gallium arsenide and the development of the indium gallium arsenide photodiode by Pearsall. Engineers overcame earlier difficulties with pulse spreading using conventional GaAs semiconductor lasers at that wavelength by using dispersion-shifted fibers designed to have minimal dispersion at 1.55 μm, or by limiting the laser spectrum to a single longitudinal mode. These developments eventually allowed third-generation systems to operate commercially at 2.5 Gbps with repeater spacing in excess of 100 km, 62 miles. The fourth generation of fiber optic communication systems used optical amplification to reduce the need for repeaters and wavelength division multiplexing, WDM, to increase data capacity. The introduction of WDM was the start of optical networking, as WDM became the technology of choice for fiber optic bandwidth expansion. The first to market with a dense WDM system was Ciena Corp, in June 1996. The introduction of optical amplifiers and WDM caused system capacity to double every 6 months from 1992 until a bit rate of 10 TB/s was reached by 2001. In 2006 a bitrate of 14 TB/s was reached over a single 160 km 99 miles line using optical amplifiers. As of 2021, Japanese scientists transmitted 319 terabits per second over 3,000 kilometers with 4-core fiber cables with standard cable diameter. The focus of development for the fifth generation of fiber-optic communications is on extending the wavelength range over which a WDM system can operate. The conventional wavelength window, known as the C-band, covers the wavelength range 1525 to 1565 nanometers, and dry fiber has a low-loss window promising an extension of that range to 1300 to 1650 nanometers. Other developments include the concept of optical solitons, pulses that preserve their shape by counteracting the effects of dispersion with the nonlinear effects of the fiber by using pulses of a specific shape. In the late 1990s through 2000, industry promoters, and research companies such as KMI and RHK predicted massive increases in demand for communications bandwidth due to increased use of the Internet, and commercialization of various bandwidth-intensive consumer services, such as video on demand. Internet protocol data traffic was increasing exponentially, at a faster rate than integrated circuit complexity had increased under Moore's law. From the bust of the dot-com bubble through 2006, however, the main trend in the industry has been consolidation of firms and offshoring of manufacturing to reduce costs. Companies such as Verizon and AT&T have taken advantage of fiber-optic communications to deliver a variety of high-throughput data and broadband services to consumers' homes. Modern fiber-optic communication systems generally include optical transmitters that convert electrical signals into optical signals, optical fiber cables to carry the signal, optical amplifiers, and optical receivers to convert the signal back into an electrical signal. The information transmitted is typically digital information generated by computers or telephone systems. Transmitters. The most commonly used optical transmitters are semiconductor devices such as light-emitting diodes, LEDs, and laser diodes. The difference between LEDs and laser diodes is that LEDs produce incoherent light, while laser diodes produce coherent light. For use in optical communications, semiconductor optical transmitters must be designed to be compact, efficient, and reliable, while operating in an optimal wavelength range and directly modulated at high frequencies. In its simplest form, an LED emits light through spontaneous emission, a phenomenon referred to as electroluminescence. The emitted light is incoherent with a relatively wide spectral width of 30 to 60 nanometers. The large spectrum width of LEDs is subject to higher fiber dispersion, considerably limiting their bit-rate distance product, a common measure of usefulness. LEDs are suitable primarily for local area network applications with bit rates of 10 to 100 Mbps and transmission distances of a few kilometers. LED light transmission is inefficient, with only about 1% of input power, or about 100 microwatts, eventually converted into launched power coupled into the optical fiber. LEDs have been developed that use several quantum wells to emit light at different wavelengths over a broad spectrum and are currently in use for local area wavelength division multiplexing, WDM, applications. LEDs have been largely superseded by vertical cavity surface emitting laser, VCSEL, devices, which offer improved speed, power, and spectral properties, at a similar cost. However, due to their relatively simple design, LEDs are very useful for very low-cost applications. Commonly used classes of semiconductor laser transmitters used in fiber optics include VCSEL, Fibre, parrot and distributed feedback laser. A semiconductor laser emits light through stimulated emission rather than spontaneous emission, which results in high output power, 100 MW, as well as other benefits related to the nature of coherent light. The output of a laser is relatively directional, allowing high coupling efficiency, 50%, into single-mode fiber. Common VCSEL devices also couple well to multi-mode fiber. The narrow spectral width also allows for high bit rates since it reduces the effect of chromatic dispersion. Furthermore, Semiconductor lasers can be modulated directly at high frequencies because of short recombination time. Laser diodes are often directly modulated, that is, the light output is controlled by a current applied directly to the device. For very high data rates or very long distance links, a laser source may be operated continuous wave, and the light modulated by an external device, an optical modulator, such as an electro-absorption modulator or MOC, Zender interferometer. External modulation increases the achievable link distance by eliminating laser chirp, which broadens the line width in directly modulated lasers, increasing the chromatic dispersion in the fiber. For very high bandwidth efficiency, coherent modulation can be used to vary the phase of the light in addition to the amplitude, enabling the use of QPSK, QAM, and OFDM. Dual polarization quadrature phase shift keying is a modulation format that effectively sends 4 times as much information as traditional optical transmissions of the same speed. Receivers. The main component of an optical receiver is a photodetector which converts light into electricity using the photoelectric effect. The primary photodetectors for telecommunications are made from indium gallium arsenide. The photodetector is typically a semiconductor-based photodiode. Several types of photodiodes include P-N photodiodes, P-I-N photodiodes, and avalanche photodiodes. Metal semiconductor metal, MSM, photodetectors are also used due to their suitability for circuit integration in regenerators and wavelength division multiplexers. Since light may be attenuated and distorted while passing through the fiber, photodetectors are typically coupled with a transimpedance amplifier and a limiting amplifier to produce a digital signal in the electrical domain recovered from the incoming optical signal. Further signal processing such as clock recovery from data performed by a phase-locked loop may also be applied before the data is passed on. Coherent receivers use a local oscillator laser in combination with a pair of hybrid couplers and 4 photodetectors per polarization, followed by high-speed ADCs and digital signal processing to recover data modulated with QPSK, QAM, or OFDM. An optical fiber cable consists of a core, cladding, and a buffer, a protective outer coating, in which the cladding guides the light along the core by using the method of total internal reflection. The core and the cladding, which has a lower refractive index, are usually made of high-quality silica glass, although they can both be made of plastic as well. Connecting 2 optical fibers is done by fusion splicing or mechanical splicing and requires special skills and interconnection technology due to the microscopic precision required to align the fiber cores. 2 main types of optical fiber used in optic communications include multi-mode optical fibers and single-mode optical fibers. A multi-mode optical fiber has a larger core, greater than or equal to 50 micrometers, allowing less precise, cheaper transmitters and receivers to connect to it as well as cheaper connectors. However, a multi-mode fiber introduces multi-mode distortion, which often limits the bandwidth and length of the link. Furthermore, because of its higher dopant content, multi-mode fibers are usually expensive and exhibit higher attenuation. The core of a single-mode fiber is smaller, 10 micrometers, and requires more expensive components and interconnection methods, but allows much longer and higher performance links. Both single and multi-mode fiber is offered in different grades. In order to package fiber into a commercially viable product, it typically is protectively coated by using ultraviolet cured acrylate polymers and assembled into a cable. After that, it can be laid in the ground and then run through the walls of a building and deployed aerially in a manner similar to copper cables. These fibers require less maintenance than common twisted pair wires once they are deployed. Specialized cables are used for long-distance subsea data transmission, example transatlantic communications cable. New, 2011 to 2013, cables operated by commercial enterprises, Emerald Atlantis, Hibernia Atlantic, typically have 4 strands of fiber and signals cross the Atlantic, NYC London, in 60 to 70 milliseconds. The cost of each such cable was about $300 million in 2011. Another common practice is to bundle many fiber optic strands within long-distance power transmission cable using, for instance, An optical ground wire. This exploits power transmission rights of way effectively, ensures a power company can own and control the fiber required to monitor its own devices and lines, is effectively immune to tampering, and simplifies the deployment of smart grid technology. The transmission distance of a fiber-optic communication system has traditionally been limited by fiber attenuation and by fiber distortion. By using optoelectronic repeaters, these problems have been eliminated. These repeaters convert the signal into an electrical signal and then use a transmitter to send the signal again at a higher intensity than was received, thus counteracting the loss incurred in the previous segment. Because of the high complexity with modern wavelength division multiplexed signals, including the fact that they had to be installed about once every 20 kilometers 12 miles, the cost of these repeaters is very high. An alternative approach is to use optical amplifiers which amplify the optical signal directly without having to convert the signal to the electrical domain. One common type of optical amplifier is an erbium-doped fiber amplifier, EDFA. These are made by doping a length of fiber with the rare earth mineral erbium and laser pumping it with light with a shorter wavelength than the communication signal, typically 980 nanometers. EDFAs provide gain in the ITUC band at 1550 nanometers. Optical amplifiers have several significant advantages over electrical repeaters. First, an optical amplifier can amplify a very wide band at once, which can include hundreds of multiplexed channels, eliminating the need to demultiplex signals at each amplifier. Second, optical amplifiers operate independently of the data rate and modulation format, enabling multiple data rates and modulation formats to coexist and enabling upgrading of the data rate of a system without having to replace all of the repeaters. Third, optical amplifiers are much simpler than a repeater with the same capabilities and are therefore significantly more reliable. Optical amplifiers have largely replaced repeaters in new installations, although electronic repeaters are still widely used when signal conditioning beyond amplification is required. Thank you for watching this video.